And once again, welcome to the November Mixer. Tonight we have two presentations on tap. Ken's going to talk about the QRPLabs filter that he modified with use with the DCR project. This is part two of this filter. And then I'm going to talk about LTspice analysis types. And time permitting, we'll do a roundtable. And if anybody has any questions that's going on, feel free to ask at that time as well. So I guess with that, Ken, are you ready to go?
Yeah, I can go ahead. Let me share here. Um, there. Do the entire screen. Pick it. Also share. Okay. You see my screen?
Not yet. Well, I see black.
Nothing.
Yeah, we got it.
Okay. As you all know, I've been trying to get the QRPLabs bandpass filter to work with the DCR. The uh, the DCR board is laid out with header spacing to fit the QRPLabs filter. Um, Dave uploaded my latest video. Um, in it, I'm demonstrating uh, the audio strength using the simple bandpass filter, and then comparing it to the QRP Labs, just like I did in the previous video. Um, the second part of the newest video is I actually modify the filter, and the audio level is the same for both, or very, very close. So basically, so this is the DCR, and here is the connector or the headers for the bandpass filter. Um, so uh, what? Where is the next slide here? So oh, it won't switch over. Let me kill this. Let me get this. So this is the This is the board for the or the circuit for the simple bandpass filter, um, split capacitor, and everything. Um, so what I did is, so this is the circuit for the QRP Labs bandpass filter, and what I'm trying to do is modify the output to work with 1500 ohms, which is the input of the chip. Presently, the labs is 50 here, and whatever it is on this side. So what I proposed to do was to modify it like this. So basically, disconnect the top of the secondary from the output and connect the top side or the hot side of the primary directly over to the output. Um, and then what I did is in the labs, QRP labs manual, what I did is I grabbed all these turn ratios for all the different bands and I stuck them into an Excel sheet, and using the primary ratio equaling the turns ratio, I calculated the primary side impedance. So I've been using 40 meters. So it's a 31 to 6. That means that the primary side is about 1300, 1335. So I went through all the bands. Um, I've got a 20, so I'll be trying that one out. But I've calculated all the bands, and they're all pretty darn close to 1500 ohms. The 2000 one's a little high, but that shouldn't be any big deal. So to actually modify it, so here's the board layout. This is the top side. inputs on this side, on the left, outputs on the right side. So basically, the secondary winding is between ground and the output, and the primary side is between ground and here. So to modify it, what I did is I lifted the hot side of the secondary off the board, so it's just floating. And what I needed to do was to get this point over to the output, which was very simple by shorting these two uh, pads together. So now what we're doing is transferring the energy to the top side or the hot side of the primary, jumping it out to the output. And if you did watch the video, the audio level that I was measuring at the speaker is the same for both filters. Actually, this one is just a tiny bit better. It's probably better tuned. So that's it. It's pretty easy. Um, at some time in the future, near future, I'm going to order all uh, the filters from Hans, and I'm going to modify them and try them out. Very simple. So this little presentation, what I'm going to do is I'm going to put it on a video as well, and then at some point we'll have all three together. I noticed that I think my first video there was like 330 views of it, so it's kind of popular, I guess. QRP Tech has been doing some chatter on using the chip for a direct conversion receiver, and they were talking about this. So they were probably looking at my stuff, my videos. But anyways, that's it. It's pretty simple. Um,
That's great. Thank you. I got a couple of questions. First off, there's a comment. I thought the modified QRP filter was noticeably different, improved over the simple one. I know you made a comment marginally, but I thought it was pronounced. But anyway, that's me. Two other comments. One is, I think you did this before, but I can't remember why it didn't work. But it seemed to me like just increasing the number of turns on the output side of that transformer would have worked, but it didn't, did it? Or did you try that?
no, I did try. I tried something else. I can't remember what it was. I'm pretty sure it would work. The only difference being is there will be more losses by doing that. Here, I'm doing a direct connection. So there will be some loss, but I don't think anything noticeable.
Do you know what the
And
impedance is on the primary side?
pardon?
So the impedance was around the QRPLabs filter's impedance on the primary side. Did you know what that was? It was stock?
Here. So for 40, 1335, I calculated.
So it's almost matching right off the bat. Okay.
Yeah,
Yeah.
yeah. It could be a little bit higher, it could be a
Yeah.
little bit lower.
Okay. My last comment before we get on to the other questions here is I'm looking at your schematic. I thought the values that you're using for the 3DB pad on the DCR seems different to me for some reason.
Which one was that?
You know, the 3DB pad on the DCR.
Where's that?
Your schematic of the DCR.
Oh, here?
Yeah. The 3DB pad. You got 77 ohms for going to ground and one.
Oh, yeah, yeah.
I seem to recall something like 250 or 249 and then 50s or 60s or something like that. Does that ring a bell?
This is the final values. I may have had other values previously. I was trying to get values so that we get about 300 millivolts at pin 6.
Yeah. Okay. Thanks, Ken. Dave, you got a question for Ken?
Yeah, just on that pad, Ken. I don't know if you remember, but you're the one that found out you needed that 51 ohm resistor. If you didn't have that 51 ohm resistor there, the pad wasn't functioning as a pad at all. So you had to have both sides terminated to 50 ohms for that to work properly. So I don't know if that's what Peter was getting at. But
Actually,
my question.
Well, just while you're on that topic, Dave, no, that I always was, I don't want to say I was uncomfortable, but I could never figure out why that 51 ohm resistor is in there, because that would change that, you parallel it up with that other resistor and that changes the value of that 3D pad, right?
Yeah.
No, it doesn't. 51 ohms, 51 ohms parallel 1500 ohms is 51 ohms. So forget about the 1500 ohms of that oscillator B pin. Just ignore it because it's, what is it, 10 times, more than 10 times the impedance. So that doesn't matter. But the filter, the pad has got to be terminated to 50 ohms. So that's all that R9 resistor is doing, is terminating the pad.
Well, what was actually happening before I put that 51 or 50 ohm resistor in there is that the source, the SIGGEN with the pad was acting as a current source rather than a voltage source. So for me to see 600 ohms, I was having to drive it at like 700 millivolts, and sometimes even slightly higher. And then I'm thinking, well, the pad is not terminated, so it's acting as a current source. As soon as I put that 50 ohm on there, then I saw that the level was down around 300, maybe a little bit more. And it just seemed to work. Now that those oscillator, what's that?
I was going to say, if you model this, because I modeled it right when you did this, I thought, oh, Ken doesn't know what he's talking about. So I thought I'd go model it. And sure enough, you know what you're talking about, that R9 resistor. If you model this, Peter, just like break the connection to C6, just break the connection, just model that in LTspice and put R9 to 1500 ohms. And then, look at what the signal level output is, and then use a 51 ohm resistor, you'll see quite a big difference. And you get the actual required attenuation once the 51 ohm resistor is in place there.
Yeah, that oscillator pin input wants to see a voltage, not a current. And that's why when you have to drive that signal coming in really high for it to put a reasonable amount of signal on that oscillator pin.
Yeah. Okay.
Yeah, because I guess another way of saying it, it's 51 ohms. All the current is going to go through the 51 ohm resistor instead of going through the 1500 ohm oscillator B pin. So it's just sampling the current, right?
Yeah.
So Ken, anyway, my question I was going to ask was, you had said you measured the impedance of the filter, and you said it was pretty darn close to 1500 ohms. How did you measure that?
No, I didn't measure it. I calculated.
Oh, okay. Because you had said you measured it was pretty close.
No, that's this chart is. So these are the turn ratios from the manual. And I just used the turn ratio to the square of the or the impedance ratio to the turns ratio squared. So I went backwards. I went from the output at 50 ohms back to the primary side of the transformer.
All right. Okay. So somebody's gonna have to bring their VNA to 4 Days at Eric's Cottage to make a measurement to see if your calculations are accurate. Then, Ken.
Sure.
I was gonna suggest that. The problem is though, the VNA is 50 ohms, so it could influence this. right?
Yeah,
Don't know.
didn't we find, Dave, through testing that the VNA probably was not too bad up to about a K, right? So if
Yeah,
you dig you,
but don't forget the Nano VNA. I think it appears as a 50 ohm device, right? So I don't know. I can't remember,
I
Peter,
think
to
it might
answer your
give us an
question.
indication. It
I
won't tell
cannot.
us any accuracy, but it'll give us an indication that it's up there. But anyway, okay.
Yeah. So I wasn't. I can't remember because I think with the probe, I don't know if it's loading down the probe because the input of the probe is so high. I can't remember.
Okay.
Don't quote me on this.
Okay. Is there any other questions or comments for Ken? Okay. Thank you, Ken. Glad to see the filter equations wrapped up.
Yeah, finally. Finally. Kevin, you going to be at Eric's?
He's muted.
Okay.
Yes, he will be.
Okay. Do you know if he's staying over the weekend or is he going to
I think so.
couple?
I think so.
Okay. Well, whatever. Kevin, bring your DCR. We'll take a look at it.
Yeah, sorry, just had to go for a break there for a second.
Yeah, no problem. No problem.
Yep.
Okay, doke.
Kevin's there for the duration. So.
All right. Thanks, Ken. Okay. I guess tonight I'm going to talk a little bit about LTspice. So I'll just share my screen here. Oh, no, that's not what I wanted. We can see that?
Yeah.
Yes, sir.
Okay. Change my glasses. It's getting bad when I can't look at the screen and it's all fuzzy. Okay. This presentation will not serve as a tutorial on the full range of analysis available in SPICE. Instead, this presentation will provide an overview of key analysis types and their respective functions. Given the importance that I find with SPICE in my home brewing activities, I hope this presentation will inspire some of you to learn how to use SPICE, or at least dig into it a little bit deeper. And the types that we're going to cover off tonight is the transient analysis, AC, DC sweep, noise, DC transfer function, and the DC operating point analysis. So the transient analysis is all about seeing how your circuit behaves over time. It's kind of like watching it in action. In other words, moment by moment. It's especially useful when your circuit has capacitors, inductors, or switches, because those components don't react instantly. They charge, they discharge, or they ramp up over time. An example would be, say you're building an RC timing circuit, or you're using a 555 timer. The transient analysis will let you see exactly how the voltage changes during each part of the cycle. And it will all show that in a minute. It's also perfect for checking how a circuit responds to a sudden signal, like a square wave input or a power-up event. So if you're working on something like an audio filter or an oscillator or even a simple debounce circuit, this kind of simulation helps you understand what's really going on during these critical moments when things are changing. So in this slide here is an example of a 555 push-to-talk circuit that one of the guys here in Kingston had came up with. And so I had trouble trying to figure out how actually it was working. So I did an LTspice simulation of it. And this analysis allowed me to, if you follow all the plots along with the schematic, it'll become clear on exactly how this circuit operates. So, in this particular case here, the red traces the triggering, the green is the push-to-talk output, and on and so forth. So you can see how all the different parts of that circuit is working together. excuse me, the AC analysis is a simulation that shows you how your circuit responds to different frequencies. In other words, sweeping a range of frequencies through a circuit and seeing what the response is. It's mainly used with small signal inputs, which means we assume that the signal is small enough that it does not push the circuit into a nonlinear behavior. And you'll see there at the setting there, it says AC1. Now there is a zero next to it, but I forget exactly what that zero spec is. But the one is what's used pretty much in all simulations, no matter what you think it should be. And I learned that lesson the hard way. Now, this is useful when you're designing things like amplifiers or filters or other RF circuits, where it's important to know how the gain or the output changes across the various frequencies. An example with the extensive use with the probe project, it would be important to know, for example, that if our signal falls off, say, for example, 5 dB at 21 megahertz, we would then have the opportunity to modify the circuit before designing the proof of concept board. Another example for use would be if you're building an audio preamp, an AC analysis can show you how well it amplifies the bass versus treble. Or if you're working on a bandpass filter, you can see exactly where the peak response happens. In short, the AC analysis helps answer what frequency does my circuit respond to and by how much. And this is just an example of two sweeps on our probe. Now it looks dramatic, the fall off there as you get up around 10 megahertz. But if you look at the scale on the dBs there, you can see that it's not very much at all. But this is the kind of result that you get. The DC sweep analysis is often referred to by the .dc command, and it's used to explore how your circuit behaves as you vary a DC voltage or a current source. It's especially helpful for understanding operating points and transfer characteristics. In other words, how one part of your circuit responds when you change something like an input voltage. For example, say you're working with a diode, and you can sweep an input voltage and plot the diode's IV curve. In other words, showing how the current increases with the voltage. Or with an amplifier, you might want to see how the bias point shifts if a resistor value changes. And it's a great way to test your circuit's DC behavior without building multiple versions. And that's what SPICE is all about. Make all your changes, get something that seems to work from a simulation point of view, and then build your prototype. Now, noise analysis helps us figure out how much an unwanted signal or noise is present at a specific point in our circuit. And it calculates the spectral density of this noise, which means we see how much noise exists at each frequency. Now, this kind of noise, you need to be aware of, it isn't from an outside interference. It's all internal generated noise, which is, all components generate noise, like your resistors, transistors, op amps, etc. They all create some noise, and this is what we're measuring. You would use this analysis when building, for example, low noise amplifiers or filters, and it lets you see how much noise is present and which parts of the circuit are contributing the most. Now, the plot you see here is typical output from a noise analysis. It shows noise power in volts per hertz versus frequency. Now, one key thing to know here is how the noise changes with frequency. At your lower frequencies, we see something that they call 1/f noise or flicker noise. And it rises sharply as frequency decreases and can dominate in audio or sensor applications. Now, one thing about this particular simulation, if I had been aware of it during the probe project, I would have used it. Or actually not the probe project, in the Phoenix project. And the reason being is after reading a lot about what comes first, the bandpass filter or a low noise amplifier, and reading the pros and cons of it, it might have been interesting. The theory I read is put the low pass or the bandpass filter after your amp, and that way you're not amplifying the noise. But anyway, this would have been a good time to have used it, but I wasn't really aware of that at the time. Okay, DC transfer function. That is, or known as a .tf, is used to calculate a circuit's small signal DC gain at the operating point. You specify an input source, an output node, and it tells you how much the output changes in response to a very small change at the input. It also gives you other two important values, input impedance and output impedance. which are great to know when you're designing or matching stages and amplifiers. Now, unlike the transient or AC analysis, this is done at DC only. So we're looking at the response zero frequency. And a good example of this would be a transistor amplifier. You can use the .tf to quickly find out the gain and how well the input and output impedances match your signal source and load without sweeping or plotting. Now, I've not used this function, but it seems to be a simple but a powerful tool for understanding how your circuit behaves around the bias point. That was one thing, doing a little bit of research on this topic, was coming across a couple of these analysis types that I've never really used, and reading up on them, thinking, I could have used that. DC operating point analysis, or the OP command, is one of the most basic and important tools in circuit simulation, and it calculates the steady state DC voltages and currents at every node in the circuit. In other words, it tells you what the circuit looks like after it's had time to settle. And on the left side of this, you can see that's the log output of the values when you run your circuit. Now, this is useful when you're working with transistors or diodes because it tells you what region the device is operating in, like whether the transistor is in cutoff or active saturation. To further explain this, the DC operating point results gives you numerical values, and you have to interpret the operating region by comparing these values against known thresholds. It's not an automatic thing here, but it gives you all the data that you need in order to determine the mode of operation for your nonlinear devices. That's also a great way to check if your biasing is set up correctly. Are your voltages and currents where you expect them to be? And if not, you might need to tweak a resistor value or supply voltages. An example of how I use it: I run the analysis, note all the DC voltages in the simulation calculated, and then I check my circuit to see how the real world compares with the simulation. So an example here is just the basic common emitter amplifier. Now, a tip here would be to use the net names at the various points of interest, and will make reading the log file much easier. So if you notice on the log file there, we have VCC, base, collector, emitter, input, output for voltages. If you notice on the schematic, all those points are all labeled. And if you didn't have those labels there, you would end up with having just node numbers. And that makes it a little bit more difficult to sort out exactly what you've got there. So use the net names, and it makes it much easier to read the log file. Okay, so this is some advanced analysis that you can do. The first one up is the parametric analysis .step command. You can run multiple simulations by varying one or more parameters, like your resistance or your voltages or capacitance, over a specified range to observe how the circuit's behaviors changes. This one I use a lot, and you can easily see from, for example, when a component value begins to distort a signal, or how much signal shifts with a different value of a capacitor. Temperature analysis, I've not used this one, but I've heard people talk about it. And this simulates the circuit at different temperatures to see how temperature variations affect performance and characteristics. The example here would be, you're building an outdoor sensor, and this simulation would be a good test to see how your circuit responds from temperatures from summer to winter. And the Monte Carlo analysis, it performs multiple simulations with random variations in component values based on their tolerances to analyze the effect of manufacturing variations and to predict circuit reliability. And an example here would be, okay, run your simulations using a circuit using 20% tolerance components versus 5%. Now, I suppose if you're in mass production, if you could get away with using a 20% tolerance component and your circuit's still in spec, well, then you're good to go. If not, maybe you'll have to spend a little bit more money and go for 5%. So in this example here, this was a Carlo analysis on our probe input capacitor. And I kind of wish I'd done this analysis on the probe project, because we knew that input cap was sensitive. It was just not how sensitive. And the analysis would have shown us to this sensitivity and would have saved us a lot of extra work involved, because we were substituting 0.1 microfarads, 5 picofarads, 1 picofarad, 0.5 picofarads. We were soldering, desoldering the different values, and then running all through all the various tests that we do to see, the effect on behaviors and stuff. So this analysis here, I just chose 20% tolerance on, I think it was the 1 picofarad capacitor. So 20% of 1 picofarad is pretty small, but you can see how much of a swing that effect had. So anyway, so there's a good use for that particular analysis. And that's all I have, guys. Okay. Oh, Howard.
That was really interesting, Peter. I don't know very much about LTspice, but that's kind of cool, all the things it can do. Can you hear me okay?
Yep.
So the noise analysis, does that take into it? Do you know if that takes into account the actual design or placement of the components, for like if you have a long lead or a short lead between two components, or does it just look at the noise generated by the components sort of in the...
It's going to be you know what, if you want to, I've never played around with this. I know you can do things in LTspice with transmission lines, but that's not what you're talking about. So I don't think I don't think there's a model in there for traces. Maybe there is, or maybe you have to develop your own. I don't know. But as far as I know, it is taken into account components only. Unless you have a transmission line put in there, then I would probably take that into account as well.
Interesting, because that'd be something if you could manipulate the locations of the components to reduce the noise, if it was able to do that.
I don't think it's so much the physical placement. LTspice doesn't know about physical placement of components. It just knows what's ahead of it and what's after it, that kind of thing. So physical placement would be, that's something else.
Interesting. Thanks.
Okay. Hello, Dave.
Yeah, Peter, good presentation. Very, as usual, very thought-provoking, because that, I guess, let me come back to Howard. Howard, for noise, take a look at my op-amp video I did. Right towards the end of it, I talk about how LTspice uses noise and how to take the output from LTspice and actually calculate RMS noise, the voltage level noise. But anyway, I'm not telling you to go do that. There's a good video that I reference, and that's how I learned how to use it. And I can't remember who does it. I can't remember if it's one of the big chip manufacturers. Maybe, I don't know. It's one of the big chip manufacturers. They did a video on modeling noise, and it's very, very good. So I encourage you, if you're interested in how to do noise analysis in LTspice, you could do that. You could simulate leads if you know what the inductance or resistance is in a lead, but that's all part of the spec. If you look at, you've got a 3904 resistor. If you go to the parameter file, LTspice has a whole bunch of things which models all that kind of stuff, lead inductance and resistance and all that kind of crap, right? But so that might be helpful for you. But
okay,
Peter,
I'll have a look at that.
Yeah, the DC transfer function, Peter, I never played around with that, but that's very, 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 very interesting. And you know why I'm saying that? Do you know why I'm saying that?
Help me out. Let me say,
because
the
to get the impedance.
Yes. Yeah.
To get the impedance, the input and output impedance, because that's something we've been struggling with, looking at how LTspice calculates or can do that. So if that DC transfer function can spit that out, that's going to be helpful. I know that the guy Fez from Fez Electronics, he also does some shows you how to go and do a impedance calculation, but he uses the .NET. He uses a .NET function or in LTspice. So
and that's
very.
And that's the one we've used, and I think the thing is, Dave, we were interested with frequency as well. This other one, the DC transfer function, is going to be at DC level only, but still, it gives you an idea what it could be or what's going on.
Yeah, and that same thing. Temp. Look at Fez. Go back. He uses the temp every simulation he does. He puts in temperature variations. He puts in tolerances of parts just to see how things are going to behave. So he's a firm believer. If you're interested in how to use temp, look at his videos.
Yeah.
Let me see. What else I was going to say? Yeah. Oh, I had got one question for you with the dot step. This is something I couldn't figure out.
Yeah.
Okay. So I don't know if you figured this out, but there's a way of doing it because I see people doing it in videos, but I could never figure out how they do it. In the dot step, how do you? There's a keyboard shortcut where you could swap between the iterations, so you only show one iteration on your screen. I know you could do it from the menu. You could go and select which step you want to view, but there's a keyboard if you've got them all displayed.
Right.
You know how you remember in your one picture you've got all the signals displayed in a range. There's a shortcut where you could step through them, and I've always tried to figure out how to do that, and I couldn't figure it out. I don't know how. I thought maybe you might know.
I wasn't aware of a shortcut for doing that. I know sometimes it's a pain, and I thought, and I'm not 100% sure, but I think I discovered one way where you could actually it would show up on your plot. So for example, you run 30 simulations on your step command or 20 simulations, whatever. It would your first, when you first look at all of them, they're not labeled. So you don't really know which value of the component that you're stepping through is causing what responses. But I thought I discovered one time where you could get it to put the labels on as to which one was which, but I can't remember how to do that.
Yeah, and as well, there's on there, if you click on the plot window and you go to the menu at the top, I can't remember which drop down it is, but one of them allows you to select the iteration. So it'll show one cycle and you could step through them, right? But it's a real pain in the butt because you have to go up and manually do that. Whereas with a keyboard shortcut, it'd be so much easier.
Okay, that'll be interesting. I'll take a look and see if I can find that, because you're right, it would be much easier to do it. And then, by the way, too, if you're used to the earlier versions of LTspice, the later versions they've changed the way you access that plot and view the individual traces. But
so I cussed you out the other day because I went and I upgraded my KiCad, and it's just, for a while I was pulling out my hair because there are certain things I had to go and say, okay, how the hell are they doing this now? They changed how this is done or where it's done, and that's a problem. Once you go and you upgrade software, they may have gone and changed things, and then all of a sudden you're scrambling to see, okay, in the last version, I used to see it by doing this, but now in this version, how do I see that?
Well, that's what you get for sticking around with version 5, which is ancient and had lots of problems. You should have went to 6 at minimum. But anyway, that's another story.
Yeah.
Anyway, so you're at version 9 now?
Yeah, something or other. I had to upgrade because something to do with the libraries. I was getting library footprints from Snap Ada and stuff like that, and it was complaining that it was no longer supported in the version I was running.
Yeah. Okay. Any other questions, comments, solutions? Okay. Well, I encourage you to this presentation, I think, was a good example of having an interest in this topic and then kind of research it and review it and go through it, because what Dave found out too, there's a couple of analysis in there that they're there, but you have no idea what they're doing. But when you're going through everything to read up on it, to present on it, you think, oh, you know what? I could have used that. That'd be a good idea. Anyway, okay. Does anybody have any concerns, questions about anything before we go to a roundtable? Oh, Eric, you jumped in just ahead of Howard.
Yeah, sorry, just one question that popped into my mind about LTspice. Does it handle like every frequency range? Like if you're modeling things that are in the microwave range, it'll handle that?
You know what? I don't know. I don't think I've ever gone above a gig.
Yeah. No, I'm just curious, like because I know there's some things that start to come into play when you're, as far as trace lengths and all that kind of stuff.
I think, Eric, because it's all, I could be wrong. Maybe Dave can correct me, but I think because it's all math, it probably will. It's just that your simulation times may go through the roof. Dave, do you have a comment on what Eric was talking about?
Yeah, you're right, Peter. 100% right. It's math. It's just doing math, so it's not taking account trace lengths, lead lengths, because as you go up in frequencies to microwaves, your lead lengths, your trace widths, all of a sudden you need microstrip. You need 50 ohms, or because you could get one of those filters, SAW filters. You could build SAW filters, all that stuff, just based on PCB traces. LTspice doesn't know about that. So LTspice is purely theoretical, and it's going to use a part in its most theoretical way. And it's going to say, yep, this part will go right up to blah, blah, blah gigahertz. And it's going to function normally. But in reality, maybe the lead lengths or the pads or the traces may impact that.
Oh, for sure. Well, once you get a VHF even. Yeah.
Right. So it looks at everything like almost ideal rather than
it doesn't
reality.
take into account, Spice does not take into account any physical locations of your components or trace sizes, wire sizes, none of that. None of that.
So it's not going to help with laying out a board, like things close together, things far apart, RF shielding, etc.
No. Now, what I think it was Howard said something earlier that made me think about this. I suppose if you put a wire in there and you substitute a wire for a resistor that has a component that has a little bit of resistance, a little bit of capacitance or something like that, or inductance on it, maybe you might be able to simulate. But you know what? That's a path I don't think I want to go down.
Well, if you look at Dave Jones, Dave Jones does that quite a bit in his videos, where he'll model a cable by putting a whole bunch of inductors and capacitance, and he'll model it and he'll say, this is what your cable looks like, and let's see how it behaves. So you're right, Peter. You could do it, but you got to know what you're doing. It's above my pay grade.
I went to, I think it was a Texas Instruments website. Anyway, they had a model of a probe, of just a basic passive probe, and I thought, okay, let's get that model and I'll incorporate that into the circuit and see how the probes, these probes will influence a circuit. And it had like 10 or 15 inductors and capacitors and all kinds of stuff in this thing just to simulate that. I thought, oh my God, this is getting too heavy. Howard, over to you.
Hi. Sorry if this is a basic question, but it's been really bothering me or annoying me that I think maybe I'm just missing something. So with that old signal generator that I was looking at restoring, that kind of taking me to different places, and I started looking at isolation transformers because I was watching these YouTube videos on how to restore old equipment. So I came across a schematic for a modern isolation transformer, and the ground plugs are connected together from the like the input to the transformer and the output, and then that's the ground. Well, I don't understand what the point is of connecting the ground pins if you want to isolate everything.
The isolation transformers, I mean, somebody can correct me if I'm wrong, but I think the original idea behind the isolation transformers was, you plug into your 120 volt circuit and your transformer is isolated. The output's isolated completely from the primary through the windings, of course, for 120. And that was because when you hooked it up to, I think they were the old AC/DC radios where one line could be grounded to your chassis. And if you're not careful, that could be livened up. But at least if you're now isolated, there's a bit of a safety factor to it. Is that what you're referring to?
Well, yeah, like I understand the logic of the isolation transformer in that it won't go back to the neutral. It's like not physically connected to the neutral if you short something. But then if the ground plugs are connected between the device under test and the wall, if you short something and the neutral is connected to the panel, like after the wiring in the house, isn't that going to create a pathway back to the neutral and defeat the purpose of the transformer?
Well, grounds for me is a safety factor. So if your chassis is probably ground. Is it a 2-prong or a 3-prong that's on your SIGGEN?
It's 2.
Kevin's got a comment there. Maybe he's got a better explanation.
Yeah, I mean, we used to, back in the day on DC drives, the common thing was to cut the ground pin off of the scope, right? Because the ground lead on your scope, if you're trying to measure a high voltage, well, it's at ground, right? So you cut the ground pin off, so everything is dereferenced from ground, but then your scope is live at like 480 volts. So the ground connection on an isolation transformer is for safety, period, right? Nothing, so that if there's a fault to ground, you want to blow the fuse or whatever. But like you said, the line and neutral, they can be swapped around and you don't care, right? Because the neutral is tied. If the neutral and line are reversed in polarity and then you plug it into your normal line, then you've got a direct short from the hot to the line and away it goes. Everything blows up, right?
Yeah. I mean, that's how I would do it, Howard. Just what your schematic is showing. That's what I would do. Because I don't want, because if the SIGGEN, if a live wire went to the chassis, you want it to go to ground and blow the breaker.
Yep.
Oh, okay.
Yeah,
right.
That's for safety. That it's for your line and neutral. It's not for like ground.
You if you didn't have that ground on the secondary, you risk if there was a failure of some component that's shorting to ground on your SIGGEN, you are now at risk that you've got 120 volts floating on the chassis that you're not aware of.
But then maybe that because I'm thinking it the wrong way. But I was thinking, let's say you short a 400 volt capacitor. Well, that's a bad example, but let's say you short 400 volts to the chassis instead of potentially 15 amps. You only have whatever the components in the device under test you're going to draw current from.
Well, I mean, you're limited by the impedance of the little transformer there, so that will limit your fault current. But you still want a ground connection in there. You want somewhere for it to go if something does short out, as opposed to your body or something like that.
Right. But I understand that. But it just seems kind of defeats the purpose of the isolation transformer.
But I think, in this particular case, you see on your SIGGEN, you don't have a ground pin. So even if you don't have the ground on your transformer, you're still at risk of if something goes wrong, you could have a live chassis. So you need to be very careful working on that.
Yeah. The isolation transformer makes you not care about whether the line and neutral on your device under test match up with the actual line and neutral in your house.
Okay, I see that.
Right. So if you've got a live chassis, like old TVs and stuff like that, you no longer care, right? Because now they're floating.
I mean, one might make an argument saying that you should replace that 2-prong plug and put use a 3-prong.
Yeah.
I
was thinking about doing that. Like,
is it a live chassis?
Yeah.
Oh.
Okay. So, I mean, that you could theoretically then tie your chassis to ground and the neutral to ground, put a proper plug on it, and you're fine.
Well, that's what I was thinking of doing versus the isolation transformer.
That's what I would do. I wouldn't worry about the isolation transformer. I would.
Yeah, because then you fix the polarity, right?
Yeah. Dave, you got a comment?
Yeah, Howard. There's Dave Jones has a really, really, really good video on how you blow up your scope doing exactly what you're saying to go and do. Because as Kevin and Peter are saying, one side of that circuit is floating, and with a AC type circuit, it's purely electrical safety. You will electrocute yourself, and if there's a fault, it'll go through the ground pin of your scope and it'll blow your scope. And that's what Dave Jones is showing you. So he talks about why you need to have the grounds and neutrals and that kind of stuff connected up. So that's really important. To me, an isolation transformer is more so if you, for example, audio. You want to isolate audio where you don't care about ground. It's an AC signal going across it, or even RF, where you want to isolate what goes in and what comes out, and you don't care about ground reference. But when it comes to AC, you have to be very, very careful, because you could kill yourself. You could damage things, right?
Yeah, that makes sense. So that's what I kind of wondered. With a two-prong, an isolation transformer doesn't really solve the problem.
No, because you're wire up your SIGGEN properly.
Yeah,
that's the best way.
Yeah.
In the meantime, I think I'll take a life insurance policy out on you. Anybody else want to join me on that?
Well, that's what made me read all this. That's what made me read all this stuff.
What was that, Dave?
We need to start a 50-50 draw. When is Howard going to go poof?
Well, I'm not used to looking at things that have 3 digits for the voltage.
Michael, you had your hand up a little bit earlier. Do you still want it?
I think I was thinking about the issue that I think Dave Jones was talking about. Perhaps was if you have a resistor in a circuit and you want to measure the voltage across the resistor, you really can't do that with a scope, because the directly anyway, because the ground pin on the scope, the ground pin on the lead is connected to the chassis, isn't it? So you can't take an oscilloscope probe and just connect it across the resistor, because of the problem that Dave was talking about, that Dave Jones is talking about.
Well, you got to care.
Sure, you can.
No.
You have to do it with the mathematical thing with the 2 probes.
Yeah, you need a differential probe.
That's how you do it. That's how you do it. But you can't take one probe and stick it across.
No, your single probe, it can only go to ground. That ground clip is ground only. You put it on another component, you're shorting that component out.
That's right. Even if, I guess, well, if you use an isolation transformer, is that still true? I guess probably it is.
I wouldn't do it. I would go for a differential probe. Then you solve your problem.
Yeah. Okay. Fair enough.
Kevin.
Sorry. Yeah. Just one comment. Whoops. Oh, shoot. One comment to add, like Tektronix made some scopes, and I have one. It's a 720p or something. It's ancient, but it was designed for this kind of stuff. Like the ground on each of the channel amplifiers is isolated from the power supply. So you can take both channels, and I think you can go up to 600 volts between channels, between grounds on the channels, and it allows you to measure high voltage stuff like in variable speed drives and motors and stuff like that. But it's a very special scope. And that's the reason why, because this ground being ground and common between amplifiers prohibits you from making those kind of measurements. So anyway, for what it's worth.
Well, I guess a bunch of guys could get together here. Another team can organize and design up a differential probe.
And you thought an active probe was hard.
I don't even want to talk about how hard that was. Engineering costs are well over $1 million. Okay. Any other comments or questions before we move on? Okay, very good. Well, let's got lots of time. Let's get into our roundtable and see what everybody's been up to. From my perspective, I've only been working on, I shouldn't say only, I've been working on the Superhet receiver board for the backplane project, and my latest version I just finished and got testing. And actually, I was testing the crystal filter and I was getting very, very poor results, to the point where I had to think about it for a good couple of hours before I finally relented, and I decided I was going to measure my crystal filter like Dave does, because I couldn't get my method, which I prefer, to work properly. So as I was gearing up to do that, I noticed, well, okay, the results are the same, which I expected, or close enough. And then I realized, oh, that's why it doesn't work. I soldered the live pin on my connection to the ground. So I had shorted out the tracking generator side of things. So that's why it didn't work. Other than that, I don't think much else has been going on. No, not really. Had a few boards come back from JLC PCB that I eventually I'll get around to, but nothing as of yet. Al, you're first up on my list.
I don't have a lot to report. My new shack is well underway. I've got contractors here building my new basement, so hopefully the new shack and lab will be up within the next couple of months. Ham radio wise, I've been dabbling along with my ZBitX, figuring that out, and just received this week a PAC 12 vertical all-band antenna to go with it. So haven't tried it yet. It just came in. It looks nice. So before it gets too cold out there, I'm gonna take it out to the front lawn and stick it up and see what it does for me. So anyhow, that's kind of where I'm going. Just playing a little bit of QRP now and rebuilding the lab after all those floods last year.
Yeah, well, that's interesting. Your Pac-12. Maybe Frank might remember. I'm pretty sure it goes way, way back to our original homebrew meetings, and I think we were starting to talk about homebrewing a Pac-12 antenna, but we never did, of course. Ken, you have a question for Al?
Yeah. Al, report back on the ZBitX and the Pac-12, especially the Pac-12. I'm kind of interested in something portable.
Yeah, I was considering actually making one, but when I saw the price and I was a little lazy right now, I just decided to make the purchase. It's not that difficult to make. Well, especially if you have machining abilities. There's just some threaded rods and sections and a coil, but the build quality was really nice. So yeah, I'll report back on it once I try it and do a bit of a show and tell if I can.
Yeah.
Oh, that'd be great, Al.
And
Frank.
the ZBitX as well. I was thinking about that.
The price was right. It was cheap, and I figured, well, let's try it.
Well, that's good. Frank.
Yeah, just a comment on the Pac-12. And yeah, you were right, Peter. We did play around with a little bit. And I ended up making my own Pac-12. And it's one that I used for many years at the trailer. And it worked very, very well. It's simple to make. And I don't even think I've got the information on it. It was on the website anyway. And because they've commercialized it now that you can go buy one. But it was a neat homebrew type project.
Yeah, that's right. Ken?
Didn't Mike MKX or Z, whatever?
MKE.
Yeah, he posted something on our group about there was a link from their group. They made them a Pac-12 or a variety of it. I should look on the groups and see if it's still there.
It should be. Messages don't get deleted. I may once in a blue moon go and get rid of some old pictures of Hamfest pictures because they eat up a lot of memory. But otherwise, the messages stay there. Al?
Just one comment. If we ever decide to do a build-a-thon or anybody wants to try one, I can offer my services for machining. So putting the threads on the ends of aluminum rods and things can make it look a lot better than trying to cobble together nuts and bolts and whatnot. So yeah, if there's any interest in that, maybe we can do something.
Okay, great. Thanks, Al. That's appreciated. Okay, Charlie, next up on my list.
Okay.
If you're talking, Charlie, you're muted.
Is it me?
I'm here.
Yeah.
Just trying to get things sorted out. Not too much to talk about. Been playing with the 3D printer for the last couple of days. Working on the backplane support structure. So for the backplane radio, I think I've finally got it all together. Final piece here that I've been messing with. So doing some measurements and so on. Play with it in more detail next week. I think that's about all to talk about.
Okay, looking forward to that, Charlie, for sure. Good evening, Cherry.
Hey, yeah, I thought you called me earlier. So what I'm doing on my bench, yeah, very interesting thing going on. Like I'm building a desktop PC right now, you know, for my son. So yeah, it's a gaming PC. So I bought some motherboard and all the stuff. So trying to assemble everything together right now. Like it's almost half the way. Still half the way remaining. Plan to complete it this week. He has been very eager to get his gaming PC. So having some fun putting everything together. And yeah, that's what I'm doing on my desk right now. Yeah.
Okay, thanks, Cherry. Good evening, Dave.
Oh, it's my turn. I was just gonna. You caught me messaging Cherry something stupid. I'll message you later, Cherry. So yeah, nothing, zero, nada, not. I haven't. This is the first time I've been actually turned on this computer and sitting in front of it, actually doing stuff. I haven't been doing anything. About 2 months ago, I took my vertical down to service it. Al, I don't know if you remember, you helped me out with a lot of the calculations on the mast, making sure I'm not, it won't topple over in a windstorm. So I took it down just to check the fatigue on it, because it's been almost 3 years since it's been up, and I thought, let me take it down and check the metal fatigue, and I cleaned all the connectors, and there wasn't much fatigue. It could have probably stayed up longer, but I used different components, just refresh everything, because we do have a lot of high winds here. So, and I shortened the coax cables. I just had some tune up. I turned on the radio, and I was able to get out reverse beacon, turned it off, and I climbed back under my rock.
Not going to allow you to go to Europe anymore. Okay, thanks, Dave. Drew, good evening.
Good evening. Hi, how are you doing? Trying to find the controls of my phone. Not a lot. Radio-wise, I took down my Meshtastic beacon that I had up on the roof for, I don't know, a year, and it didn't do much. I didn't get much receipt on it. There were people nibbling around the edges who weren't amateurs who wanted, discuss Meshtastic. So I'm changing its programming to LoRa APRS. We've talked about it at the Carrot meetings a couple of times, and there's interest in using the Meshtastic transmission method, but with APRS. So I'm going to stick it over that, because that means it's amateur, and I won't be involved with other types of messaging that might go on, just to kind of keep things clean, because I'm not really sure what Meshtastic. It's kind of like a WhatsApp for some of these conspiracy nuts, so I don't want to get into that. So I think we'll go to LoRa APRS. Other than that, nothing horribly exciting, trying to just kind of maintain the antennas for winter.
What about your balloon ventures?
Well, I broke one of the solar panels and discovered how insanely fragile these things are. So I have to take it apart to rebuild it. And it's non-trivial unless you want to really tear it all apart. So I put it away. It's working. I've got a hydrogen generator. I have enough guts to generate some hydrogen in the house. It'll be fine. Can't walk away from it, but you can do it. And I've got the pressure sensors that I can, just a manometer built so that I can measure the pressure going into it. It's been interesting to try to. Some people are now using filling 2 balloons at one time and using one to equalize the pressure in the other and kind of set it up that way. So that part is built, but I haven't done it yet. So lagging behind, I'm afraid. This retirement thing, preparing for retirement, is more time consuming than I could have ever thought.
So you're going to use hydrogen, are you?
Oh yeah.
Okay.
If you're in
Right, so
in
who
for
wants
a penny, in for a pound. I mean, if it goes up, it will be spectacular.
I know. I'm going to say, okay, so that means we got to take out insurance policies with you and Howard. So after the meeting, whoever wants to join me, let me know. Okay. Okay. Thanks.
Absolutely.
Okay.
Yeah, they do talk about a lot of these guys generate their hydrogen out back. Now, I'm not sure that's going to be that much safer because I got a lot of neighbors, and if I blow up a hydrogen balloon in the backyard, I'm going to hear about it.
Oh, there's entertainment for sure.
Oh, well, and the thing is, I'm inclined to that sort of thing. So, I'm the guy that goes up on the roof all the time, and some neighbors know it. So I'm the weird guy in the neighborhood. So, setting off an explosion in the backyard would be in keeping, but they're kind of loud.
They are. Okay.
Thanks, Dave.
Eric, good evening. You may not be there.
I always got to find the mute button first. I don't want to type M into the chat
for over
box.
5 years now. We should all know how to share screens and unmute and mute buttons just like the back of our hand.
Yeah, well, I'm not as young as you guys, right? So I can't figure these newfangled things out. Anyway, so along the same lines as Drew, I've been rekindling what I started working on at Smiths Falls, which is playing with Laura as well, with the ESP32, trying to do remote control stuff. So anyway, that's really the only RF thing that's on my bench at the moment. Maybe I could put my video on too. That would be social of me. But anyway, yeah, so that's pretty much it. I might even continue it up at the cottage. We'll see. It was helpful having some support at Smiths Falls for some of the stuff I was doing. So
Who
I
gave
might
you
continue.
support at Smith Falls?
The Laura,
Who helped?
I mean,
oh, no, my outside voice. Okay.
Yeah.
Yeah.
Anyway,
bring it up to the cottage.
So yeah. So that'll be the RF stuff probably that I bring to the cottage amongst everything else. The audio frequency stuff I've already shown. It has 4 strings, and I might be picking up a bass amp on the drive up too. So 40 watts of power should be enough for the living room at the cottage, I think, to keep up with the drum kit or whatever else we have there. So anyway,
drum kit up there.
I don't know. Man, maybe we'll have somebody doing drums. Who knows?
Okay.
Maybe I'll just bring
like most of us want to have children anymore. So pump as many watts as you want, Eric.
Yeah, I'll bring my champion 100. Okay. All right.
Sure,
Thanks.
Competition.
Right.
Well, maybe just a drum machine hooked up to a big amp or something. I don't know. So.
Okay. Thanks, Eric.
Anyway,
Frank, you're up. Yep. Frank, you're up next. And you're muted.
There we go. Well, what's on my bench has had a bit of a history, in so much as really I haven't progressed at all with it. I'm getting bogged down with the software end of this dial project, to the point of it got thrown against the wall one day, but I recovered it and put it back together and things like that.
Wow.
So I've spent a bit of time, and I've also shoved it over about a week or so ago and put it in the corner of the bench and said I'll just take a break and I'll get back to it. So it's a learning curve, definitely, and it takes a lot of resources from different areas that I have been spending time searching out and finding a little more about some of the programming. And basically, that's where I'm held up. But I haven't given up, and I'll take another crack at it. But that's about it from
We'll
here.
always try. Okay, thanks, Frank.
Okay.
Howard, how's that T41 coming along, Howard? You must be finished since you're now going to a SIG-Gen.
Well, until I got distracted by that, and now I'm going to have nightmares about it. I was ready to deal with the harmonics from the PA section from the T41. That's the last little step to sort that out, to either build a filter for it, which on the group IO is the one solution, or build the modified PA, which solves the problem. So that was what I was initially going to start working on until I ran into that SIG-Gen.
Is your PA built now?
Sorry?
Is the PA for the T41 built now?
Yeah, except the harmonics aren't acceptable. And
what I was going to say was measure it, categorize it, document it, and then build the modified PA, and so you have a documented comparison. That would be an interesting thing to see.
Yeah, that's a good idea. And the person that designed it for that, so they're interchangeable.
Oh, perfect.
Yeah, so just that, and then try to come up with a way not to use two power supplies to power the thing, and then it'll be workable. So that's the goal. And I just got distracted by that whole SIG-Gen, restoring old things, which is interesting to read about and watch the YouTube videos. But
well, you'll get there. Just wire up a 3-prong plug on that chassis and you'll be fine. And keep one hand in the pocket. Okay. All right, thanks, Howard. Okay, Ken, anything else on your bench other than the filter?
No, that's pretty much it.
Okay.
What I'm going to be doing is, like I said before, I'm going to try to get I'll make a very short video on what I presented tonight, and then get all the 3 videos together on YouTube. Yeah, apparently my first video had 335 views. I'm surprised.
Yeah. Well, you're onto something. Okay.
That's it.
Okay, thanks, Ken. Good evening, Michael.
I found my microphone. Unmute. Yes. So I've been spent almost all my time for the last weeks or so looking at the backplane audio amplifier, and that has not been straightforward. Partly, I think, largely because of the complexities of using KiCad. And so I'm going to start from scratch again today or tomorrow and rebuild some stuff. Anyway, aside from that, I have an 80-meter antenna that was sort of a V over my backyard and my neighbor's yard, and I moved the one end of it over to a tree in the front, so now it's more or less straight. And the objective was to get my DXCC on 80, and I was at 91, and as soon as I moved it, I got up to 92 within a day. So I said to my friend, well, maybe if I stay up, like this is early in the morning, maybe if I stay up, get up at 5 o'clock in the morning for the next 9 days, I'd have my DXCC, but I don't think so. What else? I did buy some of those pots, by the way, the little, the ones in the case.
Yeah. Oh, nice.
Some of those, they arrived today. And really, that's it. Not much else. I still have a DCR. I got 2 DCRs sitting here unassembled. So one of these days I'm going to have to do that. Anyway, not much else, really.
Where did you order the pots from?
Amazon.
Amazon, okay.
They came Amazon Prime within a day or 2 days or something.
Yeah. I think the best buy I had was 10 crystals I bought for $1.67, and I got delivered within about 10 days, delivery included, and they seem to work well. Out of the 10, I think 4 were great, and maybe 1 is not so. So the others are marginal. But anyway,
I want to build. I want to build the crystal, the board that you talked about weeks ago. Now I want to build that sometime and do some crystal testing myself. I just haven't done it.
Yeah, I'm gonna have a crystal conversation. I think maybe up at the cottage. I've noticed some things playing around with the crystal filter today that makes me think I need to make up a crystal filter test jig that you can easily, change things around. But I haven't quite figured out in my head exactly what to do. But anyway, for a project later on, maybe February.
Yeah, anyway, that's all I have.
Okay, thanks, Michael. Best for last, Kevin? Well, so far it's pretty good because we can't hear a thing you're saying.
See, I told you. Maybe not best, but certainly last. Well, as you know, I've been playing around with KiCad and trying to get, a little sort of mashup of the power supply board. So I was working on that too, and I'm trying to figure out why my SA won't measure bandpass filters correctly. It's more, I'm sure it's a finger problem. So, but I have the tracking generator set to -20, and the insertion loss is like 20 dB below that. So there's something I'm not doing right. This relation to what Ken was saying about the QRPLabs filter. I thought, well, I should be able to just test it, right?
Well, bring it to the cottage and we can go over it.
Yeah, bring a filter and we'll do it. I'm going to bring my assay as well. I've measured filters, no problem. So yeah, it's just a setup issue.
Yeah, I'm sure it's a finger issue. And
are you doing normalizing?
Pardon me?
Are you doing a normalizing on it? Function on it?
No. See, I should read that part of the manual.
You got to do that.
Yeah, you got to do well. Yeah, that would be a good start.
But I mean, if I just hook the tracking generator to the input, it reads -20, which is what it's supposed to read, right? So
yes.
But yeah, I have to read the manual. I haven't done that part yet. I just thought, I could just do this. you know how it is, right?
Yeah. Guys don't read manuals.
Dave, you got a comment for Kevin?
Yeah. Hey, Kevin, is the sweep smooth or is it jaggedy? Is it smooth?
Jaggedy.
Oh, jaggedy. Yeah. You've got a bad connection. Something's not connected properly. You actually have, that's a real loss you're seeing.
Put your 2 cables, the tracking generator and the RFN together, and do a sweep at the appropriate frequency, and you should see a nice smooth line.
And I do.
Then hit the normalize button. It's in the same menu as tracking generator. Hit the normalize, and then when it does its thing, then you can disconnect the cables and hook them up to your filter.
Okay.
Try that.
No, but if it's showing any kind of jaggedness in that tracking, you seeing any kind of garbage coming across, chances are it's a loose connection, or you got something that's got a lot of attenuation. It's actually maybe 50 or 60 dB of attenuation.
Well, it's noisy down. It's noisy down at the noise floor, but when where it's allowing signal through, it's smooth. So, you know what I mean?
We'll sort you out next week.
Yeah, that's what I thought. Yeah. So, anyway, or I'll figure it out before then.
Yeah.
So, whatever.
Any questions? Send a message.
No, I'll read the manual.
Yeah. Perfect. But like Dave says, check for loose connections or a bad solder joint or something like that. I mean, I had that same problem going on for over a day, really. And I'm sitting here thinking, finally I started to think about it. And then I discovered that I had soldered the hot wire onto the ground. Well, no wonder I was getting all the jagginess.
Yeah, there's that. Yeah, no, went through that part.
Yeah. Cool.
So, yeah, anyway.
Okay, good. Does anybody else have any other comments, concerns, questions?
Is anybody bringing a HF antenna to Eric's cottage?
I might be.
Okay.
I have a trap dipole that I started last year that I don't really have anywhere to set up and test. And that is a convenient place with enough geography to do that. So I've got to finish, I want to finish setting that up and tuning it properly. So in that case, I think it's a 2040 trap dipole.
Okay. No, I want to. I've got that 10-tech Scout that I bought off of Frank, and I haven't used it yet. So
I've got an end-fed half-wave I'll probably bring, Ken, and I have another HF antenna that I want to experiment with. It's not anything that's worth testing a radio against just yet, but the end-fed half-wave would certainly be fine for that.
yeah, okay, all right.
Hey, Ken, I've also got a multi-band end-fed antenna. It's got traps. It's got a tuning part on it that I got from QRP guys. I've never gotten it to work well, so I'm thinking of bringing it up and just checking all the toroids are wound properly and everything's working. So I may have an antenna there that's working.
Yeah, okay, all right. Maybe I'll just pack up my stuff just in case. And we'll see. We'll see what happens. I want to fire up that 10-tech, and I haven't used it yet.
Drew, you got a comment?
Yeah, Ken, you got that 10-tech. I've got one. One thing I found is that the connectors on the board where you plug the modules in get a little oxidized. So I bought a little thing of deoxit to kind of clean them up before I used it.
Yeah, I was watching that on a YouTube video.
Yeah, it's one thing I didn't expect. I mean, yeah, they're a great little rig. You're gonna love it.
Yeah. Okay. The only so far from what I've been watching and reading, the thing I don't like about it is the output adjustments on the bottom side of the radio.
Yep.
So it's too bad they didn't have like a little dial on the front or something.
Yeah. It's an older radio. I don't think it was as convenient.
Yeah. Actually, I remember a couple of years ago, I think I watched a YouTube video of a guy who actually put a dial on the front for it.
For power?
Yeah, for power adjustment.
Yeah, it makes sense.
Yeah. I'll have to check that out again. Yep.
Okay, good. All right. I guess that's it. We've come to the end. Any other last minute comments? Okay, great meeting, guys. And I'm looking forward to seeing a bunch of you up at our SOAREX 4 days in November event, 4 days at Eric's Cottage. And we'll see you guys then, I guess. And with that, we'll say 7-3.
Okay.
Who's going to